let me know
when you have 10 minutes.
my speaking time.
Yes.
Thanks everyone for being here this morning. Morning after the night before, so I appreciate it. And I would like to thank Herman, the organizers, for the opportunity to be here and contribute to this wonderful school. I'm going to focus completely on the issue of pair density waves. First, some historical and definitional issues, and then a transition to strong coupling pair density waves and where they do exist in the cuprate phase diagram. As many of you know, our study of density waves has been, in the cuprates, has been a long-term effort. Now, 17 years. So it used to be that in the past people would study things until they solved them, but no longer does that happen. But here we have the privilege to keep working on the same problem and making incremental progress along the way. So I have many wonderful colleagues who have focused years of their effort on understanding the density wave state in cuprates, both in and of itself and its impact on the phase diagram. Taking a leaf from Greg Bobinger's book, I want to use 3 minutes for a different subject, which is to say that for younger people in the audience, our business has been building and using these spectroscopic imaging STMs. All 3 of these are in our ultra-low vibration labs in Cornell. We use them, they're optimized for different purposes. We can use them to visualize heavy fermions in real space and in reciprocal space. One of the key things you can do with this is extract the superconducting energy gap in momentum space in energy scales which are inaccessible to photo emission. So energy resolution reaches down to about 75 microvolts, whereas photo emission is roughly 30 times more energetic in its resolution. We can do this for iron superconductors, copper superconductors, recently orbital selective iron selenide superconductivity, and of course you can use the same technique for looking at density waves. This year I'm launching a new research group. My new group has 2 labs. One is here in Cork. This is University College Cork, which is my alma mater. And the other lab is here in Oxford University in the UK. I'm not launching 2 groups, I'm just launching 1 group, but it has 2 labs. If there are people in the audience who would be interested in graduate, postdoc, or even junior professional careers in the study of quantum matter, please come and talk to me. We have a number of openings available in all categories. We have a fairly comprehensive and fully funded plan now for visualizing all different kinds of quantum matter. Density waves, topological conduit insulators, magnetic monopole fluids, topological insulators, high TC. We're going to attempt to visualize the proposed viscous electron fluid. And then I also work with Una on machine learning and on macroscopic quantum physics for fundamental reasons. If you want to contact me, my email is jcseamusdavs@gmail.com. Or Google will give you the link to this site instantly. Okay. The motivation for me to pursue the exotic superconductivity in iron and copper materials is not just to suffer through the decades of pain trying to understand them, it's to actually get to room temperature superconductivity for real economic, engineering, and scientific reasons. We need to find a metallic material upon which an energy gap opens at the chemical potential due to pairing of electrons, and a condensate forms of those electron pairs, giving us breaking gauge symmetry, giving us dissipationless, dissipationless electrical and electronic transport. There are many, many good reasons. The first person who has the patent for a commercial room temperature superconductor will become a billionaire There are many reasons why it's urgent to do this now. The one which has been emerging very strongly this year is that quantum technology people want to change from aluminium, which is basically a technical trap that they're stuck in, that they want to get out. We have some room temperature we have some approaching room temperature superconductors, copper-based and iron-based. And of course we have the new hydrogen superconductors, hydrogen sulfide and lanthanum hydrides. Their critical temperature is minus 70 degrees centigrade, which is above room temperature in Greenland and Antarctica. So you already have room temperature superconductivity. There's no physical or psychological barrier to having it. We just need to work harder. Okay, now let me remind you about the Cooper-pair density wave, FFLO state. Originally, in the early 1960s, Fulda-Feller and Larkin and Ovchinnikov examined a situation where if you would split the spin polarized Fermi surface, they imagined doing it with a high magnetic field, such that the Fermi wave vector for one polarization is different than the other. Nowadays you could do that with spin orbit coupling. Then, if you pair this electron with that electron to make a Cooper pair, they have different momenta. So the whole Cooper pair has a center of mass momentum, QP, which is the difference between the two Fermi sheets. Or the condensate is made of electrons, C dagger K, C dagger minus K plus QP. So this is a perfectly legitimate order parameter, but it's a one in which the electrons have center of mass momentum. Some of the features of such a state are this. One is that the energy gap, so that is, in my language, the gap to single particle excitations. That gap modulates in space. If you write it as an order parameter, you can write it as magnitude cosine q pair density wave dot r. So that gap should modulate in space, changing sign and passing through zero, with some periodicity, which in FFLO was set by how much you could split the Fermi surface, but it doesn't have to be. It could be any mechanism which produces this finite center of mass. And the second thing is that the actual density of the Cooper pairs themselves, I'm a superfluid person, so what I call the superfluid density, it also modulates in space. The superfluid density and the order parameter are not the same thing. They both are derived from the same fundamental state, but physically they're different phenomena. This FFLO state has never been observed directly. Now, sometimes when I've been introducing these ideas, there's a tendency among some colleagues to say, well, who really cares? If you have a density wave state, it breaks translational symmetry. That's all you need to know. Either you have a density wave or you don't have a density wave. What do the details matter, whether it's made of electrons or pairs, etc., etc.? I strongly disagree with that. If you make a simple BCS-style Hamiltonian in which the mean field has finite momentum, that's a pair density wave state, and then rediagonalize this Hamiltonian and find the new eigenstates for the electrons in this environment. That's the band structure which the pair density wave will produce. If you apply a charge density wave is a modulation of the density of electron-hole pairs, not electron-electron pairs. The potential it produces appears at a different location in the Hamiltonian. When you rediagonalize a charge density wave Hamiltonian, you get a completely different band structure. So the idea that, okay, pair density wave, charge density wave, it's just how many angels can dance on the head of a pin, that's not correct. They're fundamentally different states. And their consequences are fundamentally different. All right, now let's turn to the cuprates. CO2 is a high gap Mach insulator. The energy to doubly occupy the 3d9, the x squared minus y squared orbital of the coppers is 3 electron volts. So, if there are no dopants in there, and at room temperature, you never doubly occupy one of these sites. So the electrons are frozen in position, that makes it a Mach insulator. This is the Mach gap between the upper D band and the lower D band. That's the energy to doubly occupy 1 d(x)² minus y² orbital. But Mother Nature was very tricky when she was making this material because the 2p6 orbitals of the oxygens are energetically in between the d orbitals of the coppers. This is antiferromagnetic because of superexchange between the localized spins. Now, when you dope this compound, whole dope it, okay? Everyone says, let's whole dope our single band Mott insulator and solve that problem. From the point of view of chemistry, that's nonsense. When you dope this compound, you remove an electron from the p band of oxygen. Okay? Whatever hole has to become mobile has to derive from this chemical fact. So some strange quantum mechanical object appears here at each, where one of these doped holes resides, for a femtosecond. And then these objects are delocalized, and they produce this amazing phase diagram that we still don't understand. As a function of the hole density, you almost immediately destroy the antiferromagnetic order, but you don't destroy the superexchange energy. It's still there, near 1000 Kelvin. It just doesn't have any long-range orbit. Then you enter this unknown pseudo-gap phase, and finally you enter this high-temperature superconducting phase. Right from the beginning of this field, the proposal was that this mysterious phase is a hole-doped spin liquid. So why would that happen? It would happen for the following hand-waving reason. You originally had ordered antiferromagnet, but you destroyed the order by putting some holes into the material. But you didn't destroy the exchange energy. So each pairs of electrons could still be bound into bosonic 2e charged objects by the exchange energy, which must permeate this part of the phase diagram. So then you would end up in a soup of bosonic charged 2e spin 0 objects with doped holes which might or might not have spin charge separation. So that's just, this is one of Subir's cartoons for hole doped spin liquid. It's a beautiful idea. It would be absolutely lovely if it's true. Now there's a fly in the ointment though. In fact, there are now hundreds of flies in the ointment, which is that there are many, 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 many papers showing that this is a broken symmetry state. So that's just an empirical fact. It may be frustrating, especially to the most elegant of our theory colleagues, but it is a fact of nature that this is true. And it's true for virtually all cuprates which have been studied. So now you could have cognitive dissonance, or you could have a split in the community between the believers in hole-doped spin liquids and the believers in density waves. But there's another logical possibility, which is that this state could be both. It could be a hole-doped spin liquid which, for its own internal reasons, breaks translational symmetry. Okay? If you want, harmony in the community, that's a plausible proposal. Okay, what state could have that property? Well, the place to start, if you start from the Hubbard model, it's really too difficult. But you can start from a TJ model, which is a Hubbard model where you put U to infinity and then manually project out all the double occupancy eigenstates, giving you a functional metal with hopping, plus a strong superexchange energy between neighboring spins. And at some level this is solvable, although not in any beautiful analytic sense. Numerically you can use this technique. If you take this TJ Hamiltonian, and if you allow if you do not enforce translational symmetry preservation on the TJ Hamiltonian, many, 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 many theorists using half a dozen different theoretical techniques starting from the same Hamiltonian discovered that there is another state proximate in free energy to the D-wave superconductor, and it's a pair density wave state. This diagram is from this original Himeta et al. paper. So first of all, you do not need time, you don't need some giant 1000 Tesla magnetic field to do this. It's strong interactions which are doing this. So the pair density modulation, which is here, let's say of 8 units L periodicity, is being produced by minimizing the free energy of this strongly interacting TJ model. If this comes into existence, then of necessity, by Ginzburg-Landau and by symmetry, there also has to be a spin density modulation of the same wavelength but different phase. And of necessity, there has to be a charge density modulation of half the wavelength or twice the Q vector. That's a natural property which emerges in any and all of these models. I think it's a contentious subject of whether a pair density wave has been found in a no approximation numerical model of the cuprates. That's an open question that needs to be determined. If we make a cartoon of what this object looks like in real space, because we work in real space, and furthermore, most of these theories find that it's a d-symmetry pair density wave. So you all know what d-wave superconductivity is. The sign of the wave function changes by 90 degrees. Changes from plus to minus when you rotate through 90 degrees. But so what's a d-symmetry pair density wave? Well, the sign of the wave function, the sign of the order parameter is like this, positive and negative in one location, and then as you go through the density wave, the signs change. But it's d, so that's the same as rotating the Cooper pairs. I can't do this, but it's something like you go through half a cycle, you rotate, you go through another half cycle, you rotate back. So those are that's what this symbolizes. A d-symmetry pair density wave of 8 unit cells. There should be high spin density and very low carrier density here. And there should be high pair density here and very low pair density there. All right. Now, where did this proposal come from? You know, many of us in this room have studied the cuprates for decades. This thing is a relatively new, emerging player on the stage, a latecomer to the stage. Where did it come from? As I said, it's natural in strong coupling, and the free energy is widely believed to be close by the free energy of the Cooper pair of the homogeneous superfluid. I mean, they're made of the same metal states. One of them is just the other one periodic. The property of the pseudogap phase is that above Tc, it has a large gap near the antinodes, and it has no gap near the nodes. A large gap at the antinodes and no gap near the nodes. That is the gap structure of any pair density wave. It's a well-known fact. Therefore, you also get a Fermi arc. The Fermi arc are the single particle eigenstates of the pair density wave at the chemical potential. A pair density wave can and does yield a small electron-like pocket by folding the band structure in the way I showed you earlier. And if you do this, Mike Norman did this last year, if you do this, you get the correct quantum oscillation frequency without any tuning. You have to choose a biaxial 8-unit cell pair density wave, but then you get the correct quantum oscillation frequency. Pair density wave also gives the correct spectral function for underdoped visco family. And indeed, a pair density wave of necessity must generate a weak charge density. So these were all put forward as hypothetical motivations. If a pair density wave would exist, then one could examine whether these arguments are true or not. So that's the question. Does a strong coupling pair density wave exist in the pseudogap phase of the cuprates? That question was posed, at least to me and many other experimentalists that I've been working at a meeting that was held in KITP in 2015 or maybe the beginning of 2016. The theorists really asked us to come up with new techniques whereby you could determine whether there's a modulating condensate in this part of the phase diagram. Any questions? All right, how would you visualize a condensate? All the STM images you've ever seen, virtually all of them, except for some from the University of Madrid, are images of single electron tunneling. They're not telling you what's happening in the condensate, they're telling you what's happening in the single particle eigenstates. But here we need to visualize the condensate. So the way to do that, and Hermann is a pioneer of this business, long before I started working on it, they have made very major advances. Instead of using single particle tunneling to a metallic tip and only detecting the single electron excitations, you should use a superconducting tip. Under the right conditions, then you would detect the Josephson current, and by imaging the Josephson current, image the condensate. So Bob Dines had worked on this. We originally introduced the idea of superconducting tips, but Bob Dines had demonstrated point-like spectroscopy, and Herman's group had demonstrated imaging, scan-Josephson imaging, for visualizing the condensate. Okay. Now, I have to tell you, since it's a school, I have to tell you a little bit facts. So conventionally, if this is the sample, this is the tip, and they're in tunneling contact, so this junction resistance is low enough, and that just represents the sum over all electron quantum mechanical tunneling transitions, and you apply a voltage, then you raise the chemical potential of the tip relative to the sample. And here I have a normal tip, flat density of states, this is density of states and that's energy. A superconducting sample, this is my schematic of a superconducting sample. By the amount by which you apply this voltage, you raise the chemical potential of the tip relative to the sample, and electron tunneling occurs into these states. And the current as a function of voltage, so now you have applied a voltage, now you measure the current. The current as a function of voltage sums over all the tunneling processes. If you work it out in detail, the differential conductance, dIdV, is proportional to the density of states, provided you're at a low enough temperature and the density of states in the tip is flat, independent of energy. So this is the technique that virtually all of us use. Measure dIdV as a function of V and make an image. However, if you have a superconducting tip, there's two other possibilities. One in device nomenclature is called SIS. Superconductor, insulator, superconductor. Now you apply a voltage between the two superconductors, raise the chemical potential, and indeed you'll get a tunnel current, but it's still a tunnel current of the single electron excitations. It has no Josephson component, or very little. In this case, dIdV is not related to the density of states because the tunnel current is a convolution of two functions that you don't know a priori. And the derivative of a convolution of two unknown functions is really more or less a nonsensical piece of information. You can get some energetic facts from these curves, and I'm going to do that towards the end of the talk. Last, but definitely not least, is Josephson. You take the same sample and the same tip, they're both superconducting, but now instead of a voltage source, you make a current supply, an ultra-high impedance current source, and you measure the voltage between the two pieces of metal. So now there's no chemical potential difference between these two. The chemical potentials are aligned. The two condensates can tunnel from one to the other. That's Josephson tunnel. So provided the current being delivered is less than the Josephson critical current, the condensate Cooper pairs will tunnel. And when you reach the Josephson critical current, which is a geometrical and thermodynamic property of the junction, when you reach the Josephson critical current, then the system will spontaneously develop a voltage that you will detect. So the definition of the Josephson critical current is when the voltage appears. In this situation, dIdV is completely meaningless, right? When the voltage is finite, the Josephson oscillations are occurring at some enormous frequency, and you're averaging over some unknown phase dynamics inside the junction. On the other hand, this Josephson current here is very, very important. Okay. So now here's the engineering challenge we face. We can see the periodicity of objects we want to study. You know, that from there to there is 8 unit cells. That's a bit more than 3 nanometers. So we need nanometer resolution. If we want to find, if this is due to a pair density wave, if this is just a charge density wave, then it's irrelevant. But if it's associated with a pair density wave, we need nanometer resolution. Now, if you want to make a nanometer resolution tip, this junction resistance will be in the gigaohm range. And you know, the energy gap, let's say for niobium, is 1 millivolt. So 10 to the minus 3 divided by 10 to the 9. That's a Josephson current of a picoamp. if you substitute that in here, this is 2 by 10 to the minus 15, 10 to the minus 12, that's 2 by 10 to the minus 27, which is below 1 millikelvin. So the Josephson energy for an atomic resolution conventional tip is below millikelvin. And so, you know, either you have to have an ultra low temperature STM, or somehow you have to drive this number up. So different groups have taken different ways of attacking it. We have tried to drive this number up by driving that number up. So, of course, we also tried to drive the temperature down. We have a dilution-free spectroscopic STM. In our new labs in Europe, we're going to build 2 more of the next generation of this design. Here's how we drive up the energy gap of the tip. We reach down with the tungsten STM apparatus, and I used to say, crash the tip into the surface and yank out a piece of superconductor, but I've learned from the transition metal dicalcinate people to say, we exfoliate a nanoscale flake of visco onto the end of the tip. Here it is schematically, beautifully exfoliated, as you can see. But we can retain the spatial resolution. This is an image taken with one of those tips. This is an image taken with a different one. We can tell that the peak in the IDV has doubled its energy. That tells us we're undergoing SIS tunneling. And it allows us to measure the gap in the tip, which for these experiments was 25 millivolts. So we drove up the energy gap in the Josephson energy by a factor of 25, which is a big factor in experimental physics. We drove the temperature down to about 50 millikelvin, and then bringing those tips close to the surface, we can see this Josephson branch appear and become very robust at low temperatures, at low junction resistances. The working junction resistance was near 10 megohms, so we also had to have very great stability to keep these tips alive. So yeah, so those are the parameters now for doing the experiment: 50 millikelvin, nanometer resolution, 10 megohm junction, 256. We're going to image this current. The theory for this has been worked out by a number of groups, including Herman's. This maximum current here is not actually the DC Josephson current, but it's related to that number squared, because there's still some diffusion dynamics of the phase in the junction. But in any case, we're going to image that current. It's a very good parameter. So here's a topographic image. Here's a simultaneous image of the Josephson current. As far as I know, this is the first atomic resolution image of the Josephson current. And it contains a lot of action. Now, at this point, when you've put in all this effort, your colleagues will say to you, well, how do you know this image is an image of the condensate? You're just saying it's an image of the condensate. How do you know that it actually is the condensate? So we needed to validate that we're imaging the condensate. And we can do that because zinc atoms are known from USR to destroy the condensate within about 1 nanometer of each atom. That's been known for many years, in fact for decades. So Saki-san substituted zinc atoms in these crystals on the copper site, and we can find them with single electron tunneling, and then we can compare. Every place where we know there's a zinc atom, the Josephson current goes almost to 0. You can check for yourself. The correspondence is excellent. So this is direct a priori evidence that this technique images the condensate by correspondence with μSI. In that case, take the Fourier transform. All the STM people in the audience can see very clearly that there is a coherent density wave here. But in the Fourier transform, you see that the Josephson current is modulating, which we take to mean that the density of Cooper pairs is modulating in space, with a very sharp wave vector, and it looks like it's bidirectional, but I'll come back to that in a second. Now, what did we just do? This is a new field. I'm not certain that everything I'm saying is correct, but what we think we just did is image the superfluid density by imaging the Josephson current between these two objects. We have not detected this pair density gap modulation. And that has been a criticism of this project for many years. If you think you have a pair density wave, why don't you measure the gap modulation? All right. We wanted to do a different thing first. This is motivated by Steve Hayden's beautiful work. You know, if you believe the density wave is a pair density wave, and you want to study it, you'd like to be able to turn it on and off. But it's known how to do that. Okay, so this is the intensity of the charge modulation, which hypothetically, I mean, it could be coming from a charge density wave, or it could be coming from a pair density wave. But it's an empirical fact that when you enter the superconducting state, the modulation goes down. This is the finite Q charge modulation. And then when you turn on the magnetic field, it re-energizes again. So by traveling along this axis, you can turn on and off the density wave and see what's happening. And that was a big motivation for us. This is another picture from Herman's group in Madrid. These are vortex cores in niobium diselenide. The vortex cores are what are being produced by applying the magnetic field. So what does that have to do with a pair density? Daniel Achterberg solved that problem at Ginzburg-Landau level. He showed that if you stabilize a pair density wave surrounding the zero of the order parameter in a D-wave superconductor, that you will get two charge density modulations from Ginzburg-Landau theory. And I'll show you how that happens. So hypothesize that you have a local patch of pair density wave. This is where the order parameter of the homogeneous superconductor goes to zero. Out here, the order parameter is its average value, homogeneous, unchanged. In here, you have two order parameters. One is the superconductor, and the other is the pair density wave. So this region is called the vortex halo by experimentalists. Now consider the interaction of these two order parameters. The two simplest, I forgot to say something very important. A pair density wave is a superconductor. It breaks gauge symmetry. So neither of these things, both of these things are complex fields, but you can turn them into real fields like a density. One way is to take a product of the pair density wave and the superconductor. And another way is to take a product of the pair density wave with itself. This product would predict that there are charge modulations which are at the same wave vector as the fundamental pair density. This product would predict that there are charge modulations at twice the Q vector of the pair density. These phenomena should coexist only in the halo within this model. Furthermore, the pair density wave is decaying in space. So this function is decaying, and this product is decaying twice as fast. So this modulation has a different wave vector, and it has a different coherence. If you look at it in reciprocal space, the width of the Fourier Transform line of this modulation should be twice the width of the Fourier Transform line of that modulation, because this product is that function squared. So the line widths also are related by a factor of 2. So that's a list of the things I just told. So we wanted to do this experiment. Mohammed Hamidi and Steve Edkins did this amazing experiment, really astonishing. So here's zero field, surface of visco, at about 1 Kelvin. And you can see the precision with which they were registered to the atoms. They're going to need that for the next part of the project. They had to turn on the magnetic field up to about 8.5 Tesla to produce the vortices. And it happened that it was the winter vacation of 2017, I guess. No, 2016. No, 2017. And they had to shut down operations for about 3 weeks, and then come back in January and recover this surface. So here's the image at high field in January. Now the experts in the audience can see that I'm not cheating, because there's an atom here that had moved during the month that they were in. Otherwise, all the atoms are registered within a few picometers. That means we can subtract. You have two images perfectly registered to each other, you're allowed to subtract them. In fact, we subtracted the density of states at high field minus the density of states at zero field to find the perturbation to the density of states from the magnetic field. That's what the right-hand movie shows. There are two ranges of energy, one which was studied long ago when the density wave was discovered by Jenny Hoffman. It's down here at low energies. In this talk, I'm discussing this range of energies at the gap edge. These two images are simultaneous, but they're at different energies. I'm going to study these states. So these are the field-induced charge proportional to charge modulations surrounding the vortex cores of visco 2212. If you take the Fourier transform, it looks like this. There are two Q vectors, if I cut a line through the data, there are two clear peaks, and one of them is at twice the Q vector of the other. This one is near 0.25, this one is near 0.125. So there are peaks at two different Q vectors. I'm labeling this Q vector QP, even though I don't have independent knowledge that it's a pair density wave. I'm labeling this one QP and this one 2P. Also, we actually have a good deal of information about the line widths, because we have the line width in this direction, the line width in that direction, and we have them for the two gap edges. So we have 4 pieces of information. They show quite clearly that the line width of the 2Q peak is twice the line width of the 1Q peak, with very good fidelity. So the list of phenomena which were predicted by Achterberg, all of them were detected in the experiment, plus one more, which he should have thought of, which is that the whole thing is particle Hall symmetry, about the chemical potential. This implies, in the context of these Ginzburg-Landau theory papers, that the field-induced density wave, at least in VSCO, is an 8-unit cell biaxial pair density wave. That would be consistent with the Ginzburg-Landau analysis. It also implies that this experiment is the magnetic field control of a pair density wave. Now, admittedly, this is YVCO. We can't do this experiment in YVCO yet, but we will try to do so as soon as we can, because it'd be very important to find out if we have the same phenomenology here in YVCO as VSCO. Okay. Last but not least, the elementary thing you should detect is the gap modulations. What is a pair density wave without the gap modulations? So, we had found it very difficult to identify gap modulations until this year. Fujita-san, my colleague at Brookhaven, and my collaborator, has been working on this problem using our superconducting tip technique. And this will tell you how, I mean, our recipe is reasonably okay. This is the same technique for making VSCO tips in a different instrument in a different lab with different operators, but they can still make a good tip. Now, instead of looking at the density of the Cooper pairs, they were looking for the gap modulation. So here's a topographic image with a tip. So here was the spectrum of the surface before the tip became high TC. And here is the tunneling spectrum after the tip was made high TC. And the difference between those two peaks is the gap in the tip. And now we're going to image this function and subtract that constant to find the value of the gap in the material by using the superconducting tip, an SIS tunnel. So here's an image of the gap. It's disordered, but if you take the Fourier transform, it has 4 fairly sharp peaks. And if you don't like Fourier transform, you know, you might be a real space person, you could plot just the density of states as a function of distance along this line. That's what this is. And these are the coherence peaks of the superconductor plus the constant gap. And you can see for yourself that they are modulating in space. But if you do a more stricter analysis, you can see the energy gap, as detected by this technique, is modulating in space throughout this field of view with 8-unit cell periodicity. We were absolutely delighted to detect this. Now we can determine, you know, it's modulating in 2 directions. So we can determine, is it a biaxial pair density wave, or is it domains of uniaxial pair density? So we can find the amplitude of the gap modulation in one direction and in the other direction, and take the difference divided by the sum, let's say, at each location, and that gives an image of how unidirectional the pair density wave is. And in fact, it's quite unidirectional. There are domains of size, say, 10 nanometers, where virtually everything is modulating in one direction. Here's another one, and then there are other domains where it's modulating in the other direction. So it's more like a granular unidirectional PDW, as far as we can tell, than a homogeneous biaxial PDW. I just tried to convince you that in Ginzburg-Landau theory, if you have a pair density wave coexisting with a superconductor, you should induce charge modulations at Q and 2Q. Now we know what Q is. We can detect the gap modulation, so we know Q of the pair density wave. So now we should look for charge modulations at this Q and twice it. And we do find them, again at the gap edge in this compound, as we did in the vortex experiment. There are 2 peaks in the density of states modulation channel, as there should be from Ginzburg-Lamb. So, now we think we have detected this signature of the pair density wave by using SIS tunneling with this technique. As I said earlier, this also is a very new experiment. We're not absolutely certain of what's happening. Yes?
Séamus, it seemed to me that your measurement has a non-zero average, unlike this picture, and you have an oscillation about that.
That's correct.
And can you tell me what the amplitude is relative to the average?
So the amplitude is about, well, we can go back here. Let's not make it up. Yeah, so this is 25. So the amplitude, if I remember, the average is between 5 and 6 millivolts. And the average here would have been roughly 35 millivolts. Okay, so, any questions about the experiments? Thank you for that question.
Just
Yeah.
for clarification, so the last experiment showed that in zero field you have a coexistence of a superconductor and a pair density wave, or if you wish, so you have a superconducting state that has Q equals 0 and the modulation vector.
Yes.
In the earlier experiment you showed that you see that maybe only in the vortex core at a enhanced magnetic field. Could you clarify?
Yeah, okay.
Yeah.
That's what I was trying to do with this diagram, but thank you very much for the question. So, there are 3 classes of phenomena that we have been working on. One is the density of C-dagger. The density of this, what I call the superfluid density, doesn't modulate. We detect that by real Josephson time. Right. Another is, does the energy gap to single particle excitations modulate? For some reason we don't understand, this has been very hard to detect by previous techniques, but with this technique, it's quite clear that the gap does modulate. And the third thing we were using is the Q2Q effect.
Right.
The only real data in the vortex core is the Q2Q effect, and it's sitting on top of Achterberg's theory in order to deduce that it's a pair density.
But the fact that the pair density wave decays with a length scale outside the vortex core, I was naively assuming is that outside the vortex core I don't have it, but that's wrong.
Yeah, okay.
Can you?
Brilliant question. Thank you very much. I apologize for not explaining that clearly. Look again. Why was I making such a big deal of this? Okay. It's because it's a subtraction experiment. So we measured all of the electronic structure, including the pair density wave. Then we measured the electronic structure with the magnetic field on, and subtracted one from the other.
One
So
that catches that.
exactly. So the only thing we got was what was the effect of the vortex core. Now it appears that in the background there is also a pair density.
If I may, the last one. So
Yeah.
the fact that you do in the very last experiment, SIS,
Yes.
is primarily to enhance the resolution of.
It definitely enhances the resolution. You know, these lines are far sharper, so the energy resolution is far clearer. But I must say, and there are other colleagues as well here who have worked on this, there are still some mysteries about what happens inside the Josephson junction of a Josephson STM. I think we need some theory advice on how to fully understand this.
Just one question.
All right. Yeah.
So, if we, I guess that if we measure a higher diselenite,
Yeah.
we have a charge density wave. And
Yeah.
if we go into a superconducting state,
Yeah.
we'll also probably see modulations of.
According to Ginzburg-Lambda, you must detect a pair density wave in niobium diselenite.
But what would be the difference between the pair density in niobium diselenite and the?
Well, in both cases, since the superconducting order parameter breaks gauge symmetry, but the charge modulation does not, then the elementary thing is that the Q vector of one has to be twice the Q vector of the other. That would be the simplest thing. Do scan Josephson on niobium diselenite, you should find 6 new peaks in the Josephson channel. Right? At half the Q values of the CDW. All right, now, discussion, contentious discussion. Does a strong coupling pair density wave exist in the cuprates? Well, in VSCO it does. Okay? You're in a different philosophical situation now. It isn't, maybe if we had a pair density wave, perhaps it could be used to explain the pseudogap. This is a different situation. It is, we do have a pair density wave. What are the consequences? Yes, sir.
Before you go to finite temperature and pseudo gap, it seems from your picture that you have a dark blue region and a light blue region in the superconductor. Do you see a pair density wave only for certain buildings and not for others?
Yes. So there's a critical point here at 19%, where 5 years ago or more, we examined what happens to the density wave and the momentum space electronic structure. And there is a sudden transition, there's a disappearance of all density waves here in 2212. And at the same time, there's not a reconstruction, a transformation to a new Fermi surface. So as far as we know, and as far as our techniques can detect, there's no pair density wave on the other side. Thank you for that excellent question. All right. So if it exists, what are the consequences? Well, they're the same ones I told you. It's just that the argument goes in a different direction. If you have a pair density, it must generate a particle hole symmetric antinodal gap. It's required to. You can look it up in classic papers on that subject. If you have a pair density wave, it must produce a spectral function that looks like this. This is from Andrei Chubakov's paper. And it does. That's known from photo emission. That was Patrick Lee's argument and Andrei's argument about the spectral function. If you have a pair density wave, it should produce an arc of unbound states, because the gap passes through zero every half cycle. There's an arc when you, even at zero temperature, there's an arc because the gap is modulating through zero. And furthermore, if you calculate the area of these arcs, so this is the folded band structure due to an 8-unit cell pair density wave, it predicts a small electron-like pocket in the right part of the Brillouin zone with the right quantum oscillation frequency. This is Mike Norman's one. And of necessity, a pair density wave must generate a charge density wave from Ginsberg bandwidth. Either from itself, delta P, delta minus Q, delta plus Q, or by interaction with the superconductor. Thank you very much.
Is it just a static phenomenon, or you can have also fluctuations in this kind of
Very good question. The most important and the most scientifically critical criticism of this hypothesis, and it's a one that Patrick Lee has been subjected to for at least 5 years, is that a pair density wave is a superconductor. It breaks gauge symmetry. It should transport current without dissipation. Well, clearly the pseudogap does not do that. Okay, so either this is not a pair density wave, or, as Patrick says, it is a pair density wave, but the phase is disordered. Now, until recently, I didn't really have a strong, and where we do our experiments, the phase is rigid. You're deep in the superconductor. Until recently, I didn't have a strong feeling about the question of phase fluctuations here. But now with this observation, I start to realize that it's a granular superconductor, a granular pair density wave. It doesn't have long range order. It is actually quite susceptible to phase fluctuations, because there's no way to have a unidirectional pair density wave in one direction meet a modulating pair density wave at 90 degrees and have a net Josephson current, because the average over the phase differences is zero. So it might be that a granular pair density wave is just dominated by phase fluctuations. I have no way of proving this, but it's a new hypothesis that has come into my mind recently.
Questions, especially from students, postdocs.
Yeah.
Can you think about a way of trying to image this pair density wave in the non-superconducting state?
Ah, right. Great question. So, this way, we probably can do in the pseudogap state, because it's a high energy single particle excitation, which will be unperturbed by 50 Kelvin. Josephson, basically impossible. There's no way to get it to work at 50 Kelvin. So the most likely way forward is to do this experiment at 50 or 100 Kelvin. Great question.
Other questions? Back there.
Yeah, maybe related. So in the vortex core, when you measure, you don't use the Josephson tip.
We
use the Josephson tip.
The superconducting tip.
Yeah.
Yeah. Okay. So of course you're absolutely right. But this experiment was impossible to begin with.
Yeah.
And doing it with a superconducting tip turned out to be impossible squared. We just have not, so in principle it can be done, we just have not succeeded to do it. Because it's too hard to have a high field, a high gap, BISCO tip, subatomic resolution subtraction experiment, we just have not succeeded. But it's one of our top priorities. We need a new design, Josephson STM, to do that.
And also a question about measuring at the gap edge.
Yeah.
So what's the significance of that? Why do you need to measure at the gap edge in order to see the periodicity waves?
That's a question for theorists. It might be because the modulating gap produces the largest change in the density of states at the gap edge. But we don't know from our own work why the gap edge is so important.
Any more questions from students or postdocs? So I'm now going to open, yes, last, then I'll open the floor to senior colleagues.
Precision that undergoes from this critical point that you talked about.
Yeah.
Can you talk about what kind of Fourier precision is that?
Sure. So this is Fourier Transform STM for Bogolubov QPI. And where there are delocalized eigenstates that are dispersing, we can find them by measuring the Q vector as a function of energy and inverting it into momentum space. So we use this technique as a function of doping, starting at 6%, all the way up to 19%. This set of dispersing scattering interference wave vectors are only coming from a finite arc which does not touch the edge of the Brillouin zone. Once you go to 21%, these same Q vectors come from a complete hole-like Fermi surface surrounding the pi0 point. So the so-called reconstruction is the disappearance of an arc and the appearance of a complete hole-like Fermi surface around pi.
So,
Yeah.
could you put up your patches of unidirectional CDWs
Yeah.
again? Yes. So my question is, do these patches in any way correlate either with the inhomogeneity of the atomic lattice or with the inhomogeneity of the gap maps, or do you have any feeling
Right.
for that?
Okay, brilliant question. Can I back up and give a preliminary answer that the audience may not be aware of? There are many papers saying that the superconductivity in BISCO is heterogeneous on the nanoscale, but none of our papers fall into that category.
Right.
Because the Bogolubov QPI would never have worked unless the superfluid was homogeneous. We have always said the superfluid is homogeneous. Therefore, Mohit's question is the key question. What is producing the electronic disorder? There are correlations, but they're not in the 80 or 90% range between the properties of the pair density wave that we can see and the disorder in the gap map. So that's a very important experimental research question which is being pursued right now to find out if the gap disorder in BISCO is really disorder in the order parameter of the pair density wave. That's the only logical hypothesis actually, given the facts as we know them today.
Bernhard.
Yeah, I had basically the same question as Mohit. Consequences of this inhomogeneity.
Yeah.
And the reason I'm worried about this is that in YVCO, we do most of our experiments on YVCO,
Yeah.
which is arguably a cleaner material than
Yeah.
BISCO, right? Even there, we see you know, we see this charge density modulation, but, you know, at least in zero field, it's always short range, right? So it's always inhomogeneous. And so, you know, I'm wondering how far you can get, you know, with a simpler kind of picture in which you have sort of patches of these charge density waves, and then patches of superconductivity. And of course, there's partly overlapping,
Yeah.
right? So instead of saying, well, that the basic ground state in the pseudogap is a pair density wave, you know, we have these two competing ground states.
Okay, so that's
partially coexist.
obviously a key question, but let me re-emphasize the answer that I just gave to Mohit in a related way, and it's in an attempt to answer your question. So forget these zinc things. Let's look at a region where there isn't a whole bunch of defects. Now we're looking at the condensate. We don't have to hypothesize what the properties of the condensate are. We can see it. It's got a modulation on it, but that modulation is less than 10%. So there's a homogeneous background superfluid living here, upon which is sitting a weak modulation.
No,
So we just, the kind of idea that, so there's a lot of heterogeneity if you put the right impurity atoms on the copper side. But otherwise, we think this stuff is homogeneous.
No, sure. No, there's no doubt about that.
Done?
Yeah, well, we can discuss that.
Jörg and then Peter.
So again, these patches, right? So if you order what is in your brain is thematicity, right? Then you're asking whether I could enhance the phase stiffness by just aligning these guys when I put it on a piezo or something, right?
Yeah.
So for this, of course, you would want to know how strong is the spin, whether you can align it or not, right? Because at least the charge density wave could be aligned beautifully with strain, so it would be very...
Yeah, that's right. If the dome of phase fluctuations
Yes.
would be a function of strain, then your hypothesis would be correct.
Yeah.
I seem to remember that there's some gap modulation with the supermodulation in material. But the Josephson current is completely homogeneous across the supermodulation?
No. Right, we just defined the supermodulation to be a parasitic pair density.
Okay.
Long ago, we showed that the gap modulates in the supermodulation. That's more than 10 years ago. But the reason why it's doing it is that the unit cell dimension is modulating at that period. So I just regard that to be a parasitic property of BISCO rather than a fundamental property of the cuprates. You can see the gap modulating here, right? That's the supermodulation.
That's from the gap size.
Yeah, so this is the Fourier transform of the gap map. Here's the 8-unit cell period, 1, 0 direction. But there's the supermodulation.
And in the Josephson current, you also see?
Yes, absolutely. It was removed from the images.
Oh, I see.
We didn't cheat. It says it in the supplementary. We defined the supermodulation to be a parasitic pair density wave of no consequence.
So if I understand correctly, you in the superconducting state at a low temperature, you see both modulations, one condensate and also this PDW.
Yep.
So in that sense, it is competing in some sense. But if we think that the superconducting is has got some kind of a gene from this PDW, do they have some kind of correlation intensity? For example, somewhere else condensate is strong, somewhere the PDW is strong, then do we believe it's just competing or the superconductivity has?
I think that's a brilliant question. I don't know the answer. Okay. Several of the strategic questions here have been about what is the spatial correlation between order parameter A and order parameter B, where order parameter A is a pair density. But we've just discovered the signature of the pair density wave. We don't know the answer to most of these questions. It has not yet been determined. What is the spatial relationship between the charge density wave and the pair density wave? If they have the correct theoretical relationship, then this explanation has to be right. But we don't know.
More questions? Yes, come in.
Yeah, I have one experimental question. So when you see the homogeneity using a tip and and the gap of the tip, how important, I mean, how is the gap of the tip
Right.
This does not
A
fluctuate,
good
right?
experimentalist question. Okay. Typically what they do is the following. So you find a clean, flat, typical, you know, visco surface. They're actually very good if you get them from a good grower. And your tip is in its normal state, tungsten. Now you do a complete electronic structure map. It'll tell you the gap at every location on the surface. You can take the average. That's what this is. Right? That's the average gap when the tip was tungsten. Now when you've constructed your exotic high TC tip, you do the same thing again. That's what this is. The difference between this peak and that peak is due to the convolution of two coherence peaks. So it tells us, it's a very good measure of what is the gap in the tip, in the new tip that you've just made. Now we assign this to be a constant and proceed with the experiment. That's the answer.
Yeah, I mean the point, so because there was, maybe for the students, so in the old days, people saw atoms in graphite because they picked up the flake,
Yeah.
and there was a kind of registry between the two flakes.
Yeah.
So now, having atomic resolution with something which is a flake is a little tricky to think, right? Because, I mean, there you assume that the tip is not changing when you scan.
So we can tell from repeating the topographs that the tip doesn't change when we scan. And we can tell from the moire pattern of the topograph that the crystals are aligned. The tip crystal is aligned to the bulk crystal. But the only experiments I show you here are the ones where that's true. There are many others where it's not true, and then those experiments don't work very well at all.
You can do this, John.
You could, but life is short.
Nadine, one last question.
Yeah, so when you said you just pick up the flake,
Yeah.
and then both are D-wave superconductors.
Yeah.
So their order parameters are, the positive lobe is with the positive lobe. Can you do like a 90-degree twist and then it will be exactly out of phase, and then you can absolutely say that it is a superconductor?
So that's a deep question. If you think through your knowledge of phase locking, you could only do that experiment if you had a complete superconducting circuit from the back of the flake to the back of the sample. Because otherwise, the two positive and negative lobes of the organ parameter have no definition once the samples are far away from each other. So in principle, you could do the experiment that you're thinking of, but you would need a complete closed superconducting loop for the whole operation. And it would be very hard.
I have one last question. Actually, it's not my question, it's Herman's question. I just want to go back to it. So Herman asked a question, like in dioxide selenite, where you have charge density wave and superconductivity, where if you do the measurement of Josephson tunneling, you would see the pure density wave. So now, at the level of phenomenology, is there any difference between your observation and what would be an observation in dioxide selenite?
Yes, at the level of phenomenology there is, because when you go in and out of the superconducting phase, the induced modulations are different, whether the second phase is a charge density wave or a pair density wave. So Patrick has written a paper showing how to distinguish between those cases. So the case that Herman asked is that the parent state is C dagger C, and the induced state is C dagger C dagger. This appears to us, the parent state is C dagger, and the induced state is C dagger C. But there's a way of distinguishing between those two cases by going in and out of the superconducting phase. Patrick had written a little paper on that about 3 years ago.
Has that been done on this?
No, we can't go out of this. We can only work at zero temp. That's a job for Herman.
So there is a way, but that hasn't been tested.
Yeah.
All right. If there isn't any other question, let's then Séamus